Occam 2, although this is less likely to be on an exam for you, I wanted to show you the mechanisms for imine formation. Remember that this is incredibly similar to the oxime, the hydrazone, and the enamine formation. One thing you'll notice about this worksheet is that it's actually missing a reagent that gives us the nitrogen group. Well, we know that by breaking this C-N double bond that forms, and by adding two hydrogens back to the nitrogen and the oxygen back to the carbonyl, we can actually predict the amine that is needed. Here, we need methylamine. We'll show both the formation of the imine and then the hydrolysis of the imine. Remember that every step here is directly opposite what happens in the reverse reaction. So first, let's show the cyclopentanone in the presence of our methylamine and some generic acid. I'll demonstrate how we can use H plus as an acid and what the conjugate base then is going to look like. Our first step is protonation. Although nitrogen is a fairly good nucleophile, acidic conditions here makes the electrophile, the carbonyl, even more reactive. We talk about the probability, the plausibility of these reactions happening. Nitrogen is a better base than oxygen, so in these conditions, there's a very good chance of nitrogen being protonated. In order for this reaction to proceed, we need to wait for the opportunity where a nitrogen is unprotonated or neutral and the carbonyl is protonated. So this is why reactions like this often happen at a boil. You increase molecular collisions, you increase the probability that you get a situation like this. Now my nucleophile donates electrons to my electrophile. Acyl addition opens the carbonyl. Just to be clear, this is a CH3 group coming off to our nitrogen. We can abbreviate that CH3 group as just an end, but sometimes it's a little confusing. In some places, you'll see this mechanism reported going from this intermediate to another intermediate as in just one step, and they'll highlight it as proton transfer. But there are plausible and less plausible ways that protons are transferred. In this case, the nitrogen needs to lose a proton, and the oxygen needs to gain a proton. It's unlikely that the oxygen is going to be able to take a hydrogen from the nitrogen group. This has something to do with the angles that these atoms are bonded at and their ability to overlap their orbitals and electrons in a way that allows for the bond transfer. What's more probable is that a conjugate base deprotonates nitrogen before that conjugate acid protonates the alcohol. It's incredibly less plausible that both deprotonation and protonation happen at the same time. Now, what's the conjugate base of H plus? Nothing. So to show the deprotonation step, I simply show the NH bond breaking to the N. This is where I would typically have a conjugate base sharing electrons to take the hydrogen. But in this case, there is no actual conjugate base, but I'm still left with H plus sitting in solution. I rotated my structure a little bit. Here we see the protonation. This is what allows us to protonate our alcohol to create a good leaving group. You'll notice that in a lot of our mechanisms, leaving groups are protonated water, OH2 connected to the structure, or something like a protonated ether, essentially an alcohol connected to the molecule. Remember that this is elimination. We should see both a bond formation, a pi bond formation, and a leaving group leaving at the same time. There is a carbocation intermediate that you could predict, but that carbocation intermediate would always be in resonance with either the nitrogen group or the oxygen group in our acetal mechanisms. And the resonance form that maximizes octets is preferred, and that's this resonance form. I now have this water, and I have a protonated imine, and my final step is deprotonation. Once again, I can show my conjugate base deprotonating the hydrogen, which just means the NH bond breaks back to N. Although in this case, we could show that water acts as a base and deprotonates the imine. And there we have it. Hydronium as a byproduct, or acid catalyzed with water as a byproduct, and our imine. Now let's show the reverse reaction. Once again, this hydrolysis is happening because water and acid are present. If water is not present, then the hydrolysis is less likely to occur. It can't occur if water is not present. Again, I could have shown this as H3O+. Since it's written as H+, I can also write it as H+ and H2O. In our last step, we went from a protonated imine to our imine. So here in the reverse reaction, I'll go from an imine to a protonated imine. Now that my imine is protonated, the carbon is much more electrophilic, similar to this protonated carbonyl we had in the beginning reaction. Water acts as a nucleophile and breaks the CN double bond towards the nitrogen. Why does the CN double bond break towards nitrogen instead of carbon? Carbon is less electronegative, so when the bond breaks, it's taken by the more electronegative atom. Here we've got a deprotonation. Again, our conjugate base of H+ is nothing, so I show the OH bond breaking to the O, which leaves behind an H+. You'll notice that we're in a very similar spot to where we were last time in our forward reaction, where I've got this hemiamine, if you will, because it's halfway to the production of the imine. This is analogous to the hemiacetal functional group. And I've got H+, which is a byproduct of this deprotonation step. I don't want my oxygen to act as the base, otherwise I reverse my step. So in this process, because I'm trying to remove the nitrogen from the molecule, I need to protonate my nitrogen and make it into a better leaving group. I now have an amine attached to my structure, which makes elimination easier. CO double bond forms, which allows the CN bond to break back towards the nitrogen. In forming that CO double bond, I get back to a protonated carbonyl. And again, that's exactly where I started in my first reaction. So now I simply deprotonate the carbonyl. I get cyclopentanone, H+ catalyst, and methylamine as my byproduct. Same thought process, same procedure, same flow. The only difference here is that in the formation of the imine, we don't have to follow this elimination step with a second acyl addition. During our acetal formation, we did have that second acyl addition.